All right, we are now live and recording. We're gonna go to share screen again. Share this one. All right. So we're really looking at predicting the pH of the solution, whether it's acidic, basic, neutral, and then we're gonna use the same principles to think about how we can find the pH of a buffer solution. And a lot of this stuff is gonna relate to what you guys have done in labs. Hopefully you're gonna start to see some pretty strong connections. So our next question, so we already worked through this problem. We can do an ice table, right? At the end of our ice table, we're gonna have what we have every single time, x squared over the initial concentration, making the assumption. Did you all check your assumption and make sure it was valid? Thumbs up for we checked our initial is decreased by less than 5%. I see a couple thumbs down, okay. Please make sure to check the assumption. If on, let's just say I mess up on our next exam and I give you an L problem on the exam that is not solvable by the assumption, you need to let the first person who takes that test needs to let me know before you just get it wrong. And you're gonna say, I checked the assumption, it doesn't make 5%, because then you're not gonna be able to get the right answer and it's gonna mark you wrong. So always just check that assumption, please. Okay. So our pH is 2.872. We have a solution of acetic acid. It's pretty simple. So now what we're going to do is we're going to add a common ion to the solution. Common ion means in our ice table, we have an ion on the right side that shares a conjugate acid base pair with the initial weak acid that we had. And I love that we have someone out in the wind. Is that Taylor out in the wind? It's fantastic. So if we're going to add sodium acetate to this solution that already we calculated, right? pH of 2.872. It's an acidic solution. We're going to add sodium acetate. What's going to happen to the pH of the solution? Is it going to go up? Is it going to go down? Is it going to stay the same? Go ahead and click in your answer. Couple more seconds. No calculations yet. All right, let me take a look. Mixture, kind of all over the place. A lot of people are saying pH is going to go up. Some are saying it's going to go down. Some are saying it's going to stay the same. How do we answer this question? Let's do 1 minute in breakout rooms, and then I'm going to ask for volunteer. All right, so we'll do breakout rooms, open all rooms. See you in a minute. Did you guys even talk in your breakout rooms? You're supposed to stay there for a minute.
I'm not gonna lie, I didn't mean to come back. I'm on my phone and it popped up when I was clicking on it.
Ridiculous. All right, so let's have a little group here. So is the pH going to go up, down, or stay the same?
That's a very good question. What do you think, Dr. Bailey?
That's cheating.
What's your logic? That was obviously very unsuccessful.
I said that it would increase. But
why?
I don't know.
Oh, sorry, Diana.
All right, I think everyone's back. So the point of that was to send you out and give you 1 minute with a countdown timer to come back. And then a third of you just came back. So I don't know that that worked out very well. I wanted you to get a chance to discuss without me being there to like put pressure on you or something. I don't know.
You felt like we had it figured out, Dr. Bailey.
I mean, you guys can figure this out. You got enough smart people in this group.
No, I said we felt like we did have it figured out. So that's
That's
why
why you came back. You're just like done, nailed it. Okay. Can I hear from? Let's hear from Alexandria. What did you think? Is the pH going to go up, down, or stay the same? And why did your group decide that answer?
I didn't break out into a group because my connection is kind of crazy. So I was kind of in and out, but I did say that it increased, and I thought it increased because I thought that sodium acetate is a base. So I thought maybe it would increase.
Fantastic. So I like your logic. I think my screen is still showing. Is that true? Still seeing my computer screen. So if we add sodium acetate, we go through the steps we did last class, CH3CO2 Na. We put that in water. That breaks apart as a salt, and it generates CH3CO2 minus plus Na plus, and both of those are aqueous. And what I want you paying attention to is what Alexandria said, is that what we're making is the same conjugate base of our weak acid. So we take a solution that has just a little bit of our conjugate base, right? X is the concentration of our conjugate base in the ice table, and that's a really small number. So now we're saying we're going to beef that number up. We're going to add a lot to it. So now we add a base to a solution that's acidic, and so the pH is definitely going to increase and go up. So let's think about how we calculate that. This is also part of the Chatelier's principle. Hopefully you all watched that amazing video by, shoot, what's that guy's name? Super smart dude, YouTube
Isn't
video.
it John Green?
Yeah. So that video hopefully give you some insight to this. There's a couple different visuals. So if we're adding products to a reaction that's at equilibrium, in order to decrease that pressure, that strain on the reaction, the reactants increase in concentration by consuming products. So that means we're going to use up some of our, both of these in order to make reactants. That means we're decreasing the concentration of H3O plus in the process, which means we're making it more basic, is another way to think about it. All right. So the next question is, what is the pH of a solution that has that initial solution we talked about, that had a pH of 2.872, right, with that acetic acid, and then we added the exact same concentration of sodium acetate to that solution. So I'm going to send us into breakout rooms, and I want you to work in your group to try to figure out what ballpark should it be, and maybe figure out what the actual pH itself should be. So I'm going to give you about 3 minutes to talk about this, and then we'll bring it back for a bigger discussion. And please do chat. Alexandria, are you able to try to join?
I'm just kind of sitting here. I don't see anything.
It doesn't pop up on your screen with the join groups?
No, it didn't say join the group. I'm just kind of just hanging here. I just see the clicker still up. And it looks like somebody else is back too. I don't know.
Yeah, it looks like Josh somehow popped out. Josh, what are you doing here?
Oh, he left again.
He's there.
Oh, no, he's back. I don't know.
I'm gonna sign him to group 3. Maybe he lost his connection. I'm gonna try to do this again. Do you get something on your screen now, Alexandria? Josh, go.
I hit that by accident.
All right, we got 2 answers. I'm kind of curious to see what these answers are. All right. We'll wait till everyone's back, then we're going to talk through this. Sam, I got to ask about the fish. Is it a balloon?
Is it what?
Is it a balloon?
No, it's a mount.
And it's just like hanging from the ceiling?
Yeah.
That's amazing. Did you catch it?
Yeah, I did like 4 years ago, I think. 4 or 5 years. Thank you.
All right, looks like everyone's back. So we'll stop with the squirrel conversation, but that's fantastic. I mean, fish conversation, but squirrel. So I heard some really cool conversations about how to approach this. So can I have, let's see if Sydney McCann, you want to share what your group had as a potential approach? And there's no right or wrong answer. We're just talking about ideas that might work.
We didn't really get that far. We just set up like the ice table and then wrote out the Hasselbalch equation.
Okay, so which one do you use, an ice table or Hasselbalch? Hasselbalch.
Do you not use both?
So it's one or the other. So let's talk about that. In the conversations I heard, a lot of people were saying, well, we know that acetic acid makes H3O plus. We know that acetate makes OH minus. So what happens if you have both in the solution? How do you figure out what the concentration of each of those is going to be? So I'll show you the hard way, and then I'll show you the easy way. So the hard way is a nice table like you guys talked about. So you have your initial concentration of both your conjugate acid base pair, and those are both shown as being equal from the problem that we started with. We know the pH is going to end up being higher than 2.872 because that's what we started with only the weak acid, and we know we've added a base to that, so the pH is going to be higher. To answer a problem like this, you have to put in 0 as your H3O plus concentration because that's what we're going to solve. That's what's going to be formed, and that's what we're going to find. So then what do I put as my X's in the change column? Where do I put a minus X? Where do I put a plus X with what's written in the initial concentrations column right now? Can I hear from Tina? Based on what you see here, what would you put for minuses and pluses for your X's?
We talked about putting minus X for HA and then plus X for H3O, but I don't know why. I don't know about A minus.
Okay.
I think we said
So
a plus
if we're-
X, but I'm not sure why. I think.
Yeah.
So let's think about this as a conservation of mass. If we're saying we have to use up our HA, that's a minus on the left side. What does it have to be on the right side? Yeah, Sarah Ray's giving us a little plus sign. So conservation of mass says if we're using our reactant, we're going to have to form both products because that means that our weak acid is dissociating into those two things. And the only reason that this is true here is because we defined, that's weird, let's get out of that. We defined the initial concentration of H3O plus is 0, and that's so that we can find what that is. So if we put it, our Q is much smaller than K because Q is equal to 0 right now. So to get to equilibrium, we're saying the reaction is going to shift to the right. So then the rest of the ice table is just like you would do normally. But our Ka value is a bit more complicated, right? Not only do we have to do a quadratic, I think this is even more complicated than a quadratic. So then I heard a question, I'm trying to remember now who asked me the question about the X's. Who was that? Lauren, can you tell me what you asked about the X's and what our conclusion was?
Well, I asked if the change in concentration for HA and A minus would be negligible for both. So if we could assume both of them would be small enough that we could not have them in the equation.
And that would simplify our equation a lot, because that would end up with 0.100 times x over 0.100. And so our answer was yes, let's try. And we can always go back and verify or validate that assumption later. So we're going to make that assumption. That's why I'm crossing out those x's. It is not mathematically relevant to cross them out, but we're making an estimation, an assumption. That's why we're saying that we're going to ignore those for now. But then mathematically, the 0.10s cancel out if we make that assumption. So then what is our x value equal to in that case? Ka value. So here's one of these really interesting points that you have already worked with a number of times in your titration labs. This is the pH at half equivalence point. This is the point at which your concentration of your weak acid and its conjugate base are exactly equal to each other. That means that half of your solution is the acid, half of your solution is the base, and it's a conjugate acid base pair. At that point, you're always going to have x equal to Ka. And it's because the assumption and then the concentrations mathematically cancel each other out. So then what is our pH in this case? Not mathematically, but if we have negative log of, so it's negative log of x equals negative log of Ka. Does that look familiar? pH equals pKa. You did that in your lab this week, right? The half equivalence point of a titration, that means you've converted half of your weak acid into its conjugate base. So we're saying right now, we just put them both together in the same solution. In your lab in titration, you start out with everything being your weak acid. And then through a strong base, you're converting half of that by using it up into your conjugate base. So now you have a 50-50 mixture of your conjugate acid base pair, and that's when your pH equals your pKa. And from the titration curve, you can find that. That's where it flattens out before it ends up going back up again. So that halfway between where it has that really steep part and where you start, that half equivalence point is where your pH equals your pKa. So numerically, this one ends up being a pH of 4.745. And remember that that is the pKa for this particular acid. For acetic acid, pKa is 4.745. That means that at the half equivalence point, or an equal concentration of our conjugate acid base pair, the pH is equal to that. So remember before in our class, I said, if you just have a solution of your weak acid or your weak base, you're always going to say, is the pH going to be higher or lower than 7? And now we have a new point that we're going to be comparing it to. So if we have a mixture of our conjugate acid base pair and we have both of them in solution, if we have an equal mixture, pH is going to equal pKa. If we have more of our base, we're going to have a higher pH than pKa. If we have more of our acid, we're going to have a more acidic pH than the pKa. So now you have 2 points of comparison. One, is it just an acid or base by itself? Compare it to 7. Or 2, if you have a buffer, a mixture of a conjugate acid base pair, your pH is always going to be compared to the pKa. Depending on which one you have more of, it's going to be more on that basic or acidic side of the pKa. So did we forget anything? Lauren, did we forget anything?
We didn't check to see if we could assume x was 0.
Yep. So if we go back and look at our values, 1.85 times 10 to the negative 5th, if we compare this to our initial concentrations, you'll find that that is a very, 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 very small percentage. So the approximation is okay in this case, it is less than 5%. So remember to do that, we take 1.85 times 10 to the negative 5th, divided by 0.100, multiply that by 100, and we'll find the percentage. I think this is like 0.0018% or 0.018%. It's a very small percentage. So we're good.
Just to be clear, did you get the Ka from like the references?
Nope, it was the first problem. It was written on the problem.
Oh,
That's how
okay.
we found the 2.872 pH.
Okay, yes, okay.
But yes, I mean, we could have done that. So on an exam, I will give, on an exam, the system gives you a reference guide, and you can click on that, and it has all your pHs, sorry, pKa's listed there, and Ka's.
Okay, thank you.
So whenever you're doing the homework too, I heard someone say this recently, if you're doing your homework, don't go look up the value on some other website, use the references, because those Ka values change slightly depending where you look, and they're assuming you're using their list of Ka values. So be very careful about that. All right. So our assumption is valid, 0.018%. Okay. One thing to do, we can always check to make sure that our number makes sense as well. And so we can plug our X value back into the actual Ka equals expression and verify that that number makes sense. So remember, we had originally Ka equals 0.100 minus X, and then I guess it was plus X on top minus X on the bottom. What you're going to find in your calculators, if you put 0.100 minus 1.8 times 10 to the -5th, it's going to be 0.100 when you round to 3 sig figs anyway. And if we put those numbers back in, we're going to find that all these numbers give us the Ka value back. So it's just a way to kind of double check by plugging the numbers we found into the one we were solving for, the unknowns, and it validates our answer. Okay, the easy way is a Henderson-Hasselbalch equation. So Sydney said we do both or some version of them. We do one or the other. So the thing that the Henderson-Hasselbalch equation does is it basically makes the assumption for us and simplifies that equation. Now here's the problem with that. What if the assumption is not valid? So a lot of times what you'll find is if you have a very small concentration of both or a very small concentration of one or the other, the assumption doesn't work and the Henderson-Hasselbalch doesn't work. So in order for the Henderson-Hasselbalch to work, we can have a 1-to-1 ratio, we can have a 2-to-1 ratio, we can have a lot more of one than the other, but once we go more than 10 times the concentration of one of them compared to the other, that assumption no longer works. So if you have 10 times more acid than base, that's the extreme limit. If we have 10 times more base than acid, that's the extreme limit. If we have 11, 12, 15, 100 times more of one than the other, the assumption no longer works and we can't use a Henderson-Hasselbalch. So let's take a look at this equation and where it comes from. So we have the Ka expression, the generic one is up here on the screen. I want you to, can I have someone tell me how we rearrange this equation? And by the way, if you notice, I'm very deliberate on using these two interchangeably because everything we do is in water and H+ ions don't exist by themselves. Every H+ ion is always associated with water. So these things are the same thing and you'll see them represented both ways. So I want to kind of like show you over and over again that we're going to use either one. So how do we rearrange that Ka equation in order to have H3O+ equals? What does that end up becoming? Any volunteer? Can I have the cat volunteer?
Would it be Ka times Ha divided by A negatives?
Yes, exactly. Okay, now let's take the negative log of everything and see what we get. So if we take the negative log of the left side, what is that? Negative log of the
pH.
concentration of H3O+, fantastic. So the left side is pH. And then the right side, what we did is we kind of split it up. And there's some logarithmic rules that you may or may not be familiar with. If we have log of A times B, that's the same thing as log of A plus log of B. So it's a kind of distributive property of logarithms. So what you see above here is negative log of this plus negative log of the fraction HA over A minus, okay? And this fraction is going to become really important because we're going to be talking about, remember I said that ratio can only be 10 to 1 in one direction or the other, and then the equation no longer works. So that fraction right there is going to be really important. One of the other rules about logs is if you do log of A over B, then you can invert the sign. And if you do, then that would equal negative log of B over A. So by changing the sign in front of the log, that flips your fraction. So probably more than you want to know about logarithmic rules, but it's going to help you follow what I do next. So I simplified. We have pH, we have negative log of Ka or pKa, and then we have negative log of the weak acid over its conjugate base concentration. And then the last thing we're going to do is the Henderson-Hasselbalch equation. They decided they wanted a plus sign here instead. So that when you change that from a minus to a plus, it flips that fraction. So the Henderson-Hasselbalch equation itself is exactly what we had above, but see there's a plus symbol now, and these two are on opposite sides because the negative sign inverts the fraction that you have in the parentheses. So really, this equation, the Henderson-Hasselbalch equation, is a super simple way to say, what is my pH? Well, it depends on my conjugate acid base pair, what the pKa of that is. In the case that we just looked at, that's 4.74, I can't remember, 5 or something like that. And then it's based on the log of the fraction of base over acid. Once again, this only works for a conjugate acid base pair. If you don't have a conjugate acid base pair, remember one proton different. This is a question Jesse asked last class. It has to only differ by one proton. If you have two protons different, you can't use this equation. So here we say, if these two are equal, let's use that as an example. And I actually might have that question. Let's just go ahead and talk through that. If these two concentrations are equal, if, like the last one, right, we had these two concentrations were equal to 0.100 molar, what happens to that pH equals pKa plus 1? What does the fraction become if those two are equal to each other? Samantha, what does the fraction become if it's the same number divided by itself? Samantha, can you hear me? Are we losing internet connectivity? There we go. Oh, we had you. Clicking back and forth. All right, we're gonna come back to it another time when your internet connection is more stable. Do we still have Taylor number 2 there with the ceiling shot going?
Does that mean Taylor Arnold?
Taylor Arnold, I know. But I'm just calling you
sorry.
Taylor.
I'm sorry, what was the question?
So what is this equation? What happens to the A minus over HA when we have the same concentration of both?
Oh, it just becomes 1.
And what's the log of 1?
0.
So at that point, we end up with pH equals pKa plus 0. So basically what this equation does is it says, what's the ratio between our conjugate acid base pair, right? What is this fraction? And based on that fraction, we're either saying it's more basic than the pKa. If it's more basic, it's gonna add on to the pKa. It's gonna make it a higher pH. If it's more acidic than a 1-to-1 mixture, it's gonna bring the pH down. So this equation is a really simple way to kind of bring it all together. Do we have any questions on that equation as of right now? So this is kind of walking through all that. Questions? You want to see if we can use it? So going forward, if you know you have a mixture of a conjugate acid base pair, are you going to use the ice table approach or are you going to use the Henderson-Hasselbalch approach? Number 1, ice table. Number 2, Henderson-Hasselbalch. Show me fingers. 1 or 2? I would absolutely say number 2. I'm going to disagree with anyone holding the 1 up because don't waste your time doing an ice table. Just do the Henderson-Hasselbalch. If you have a mixture that isn't an extreme difference, right? If you have 100 times more base than acid, you can't use it. But most of the buffers you're going to see are pretty close to 1-to-1 or 2-to-1 mixture. So keep that in mind. All right, so let's go ahead and do the calculations for a buffer. So I'm going to send you to breakout rooms. And I want you to work through this and chat with each other. If I can just get my screen.
Is this
Allow
not
me.
Hasselbach?
This is Hasselbach, or it can be. Go ahead and open the room so you can work on it and chat through it, all right? See you in a minute. Couple minutes. Taylor, you able to go? I signed you to room. Sweet.
Only one's back.
Has everyone clicked in their answers? We only have 9 responses. All right, we got everyone back. Looks like it. All right, let's do the logic check before we dive into any of this. I want to hear from Patrick. How are we gonna give ourselves a rough idea of whether the pH should be higher or lower than a particular number, so we don't mess up on some stupid calculation and then end up being in trouble afterwards? What do you think, Patrick?
Decide which ones, like how much their base and acid there is.
Okay, and so which ones did you decide? What do you decide is an acid? What's a base in this?
So the formic acid is the acid, and the potassium formate is the base.
Okay, so our conjugate acid base pair, this one is our base, and then this one is our acid. And remember that CO2H can also be written out as COOH. Both of those are very indicative that it's an acid. Okay, so that gets us thinking about which one's an acid, which one's a base, but then what do we think about compared to a specific number, we expect it to be higher or lower? What number are we going to comparing it to, and do we think it should be higher or lower before doing calculations? Patrick, do you want to answer that, or do you want to pass that on?
We expect it to be higher than 0.30. Well,
Higher than the molarity, or?
Yeah, higher than molarity, because it's more. There's more base there than acids.
Okay, so I like that you guys are comparing the concentration of acid to base, but I want to focus in on a number that's going to say it's going to be a higher or lower pH than something, because there's more of the conjugate base than the acid in that conjugate acid base pair. So can I get another volunteer to say what number we're going to compare that to be higher or lower than? Is it going to be higher or lower than pH 7? Is that what we're comparing it to? Can I go for Sydney Chastain? Are we expecting the pH to be higher or lower than 7, or are we comparing it to a different number?
I'm gonna guess lower than 7. That's just a guess.
So I'm going to call out and say that we're not comparing it to 7 at all. So what number are we comparing it to? Any volunteers?
Would it be the pKa?
So Verda just said the pKa. So the pKa for this particular conjugate acid base pair is equal to 3.76955. It's probably way too many sig figs. I should probably have fewer. So if we had an equal mixture of the conjugate acid base pair, both of them are 0.30 molar, we would have pH equals pKa. In this case, we don't. So we're going to go back to what Patrick said, and he said we have more of the base than its conjugate acid. So does that mean pH is going to be higher than pKa or lower than pKa?
Higher.
It's going to be higher than pKa. So we know that pH is going to be greater than 3.77. That's our starting point. Every time we do a buffer problem, make sure to do that. Because sometimes you might flip the fraction at the very end of the Henderson-Hasselbalch, and if you do that by mistake, you're going to end up the exact same difference on the wrong side of the pKa, so you have to know which side you're supposed to be going on. All right? So in this case, if we write it out, we have pH equals 3.77 plus log. When it's a plus log, remember it's always the concentration of the base. And the reason that this is a base, HCO2K plus water, gives us HCO2 minus plus potassium plus. And it's a 1-to-1 ratio. It is completely soluble, so everything that starts here ends up as our conjugate base. So we're going to do plus the concentration 0.52 over 0.30. And when we do that, we end up getting the pH, which is plus log 0.52 over 0.3, which ends up giving me 4.01 as our pH. How does that compare to what our class values were? Only 16 people that clicked in. People forget to click in. So here's a great example, the 3.53. If you got that number, it means you probably flipped that fraction and put the acid over the base, or you had a minus sign instead of a plus sign. So if you did that approximation first and said it should be higher than pKa, pKa is 3.77, you're going to save yourself that error. I'm going to go ahead and stop this poll. 4.01 is a very reasonable answer. Would we want to do an ice table for this? I wouldn't want to do an ice table for this, right? We could, and it'd be all this mess, but I'd much rather just do Henderson-Hasselbalch, which is this last part over here. All right, we are doing pretty well on time. So what I'm gonna ask us to do is work through finding the pH of some of these buffers here based on the table above. So our first one is going to be using acetic acid again. And we're gonna go ahead and I want you, just with the information provided here, I don't think this is on the worksheet for today. Correct me if I'm wrong. I think this is past the worksheet, but that's probably should have added a little bit more to it. Go ahead and figure out and estimate what the pH should be, and then go ahead and click in what the pH is once you calculate it. Do y'all want to be in breakout rooms, or are we good? Give thumbs up if you're okay. If you want to be in breakout rooms, give like a thumbs down or something. Taylor, that is a totally useless thumb because I'm pointing from the bottom. Miss Arnold. Okay. I think we had a mixture. We're not going to do this one in breakout rooms, but I'll do the next one in breakout room, okay? And when you found your answer, go ahead and click it in. All right, we've got 5 responses. Make sure when you find your answer, click it in. Let's do about 30 more seconds. All right. I'm gonna go ahead and take a look at the answers and see how much of a mix we had. So it looks like a third of the class did 4.45, we did 4.49. Ooh. We have a lot of values all over the place. So some as high as 12, some 5, some 1. All right. What that tells me is we're not feeling super confident on this yet. Is that a fair statement? So can I get someone to share how they worked through this? Nick, I haven't heard too much from you today. Do you mind sharing how you set this up and how you work through it?
Yeah, actually, honestly, I wasn't really too sure. I was kind of getting this mixed up.
All right, so what was your thought process? What might you use? What do you recognize? What information do you have?
So weren't we looking for the pKa value at first?
Yep.
That's the thing. I guess I wasn't really sure what I was looking for to begin with. I thought it was the pKa value.
So we have acetic acid pKa value right here. Oh, sorry, I'm not sharing my screen. Am I sharing my screen? I am sharing my screen. So what do you do with the pKa?
What are we going to divide it? I guess that's why I got mixed up on. I thought we were dividing it, or we were going to use a 0.50 moles of acetic acid and then divided by, or I'm sorry, divide the base by the acid.
Okay. So 0.25 is the base over the concentration of the acid, 0.50 molar. And what do we do with that? How does that help us?
And then we're trying to find the log value of that. Is that right?
Yep.
Okay.
And then what do we do with that?
And is that when you add the pKa value to that? Okay.
Absolutely. So that is the Henderson-Hasselbalch equation in action. So we're saying the pKa is 4.75. We know that that would be the pH if we had an equal mixture of both. We don't. So are we expecting the pH to be higher or lower than the pKa? Nick, you want to answer that one?
Oh, I'm sorry. What was the question?
Do you expect the pH to be higher or lower than the pKa in this problem?
Should it be lower?
Why?
Is that because we have more acid than base?
Yes. So of our conjugate acid base pair, we have more of the acid than the base. So pH is gonna be lower. So if we get a pH value that's 5 point something, we know that we messed up and we might have accidentally made this a minus sign, or we might have flipped these or something like that. So if we do this calculation, I believe, one of the things that you might find if you get really wonky numbers is you might need to use parentheses. So when you take the log of something, make sure to take the log of parentheses 0.25 divided by 0.5. And if you do that, you should end up with a pH value of 4.45. Does that seem okay? And if we end this, what do we get for our clicker responses? 4.45 was the majority response, but only 2/3 of class got that. So once again, if you get something that's higher than the pKa, we know that that's inappropriate. And it looks like a couple of these 5.0, that's probably if you flip that fraction or use a minus instead of a plus. So always estimate beforehand. And then we have some others that are maybe a rounding difference right there. Okay, so our next one is ethyl ammonium and ethyl ammonium chloride and ethylamine. I'm gonna send us into breakout groups and I'm gonna jump around between the groups. If I can just get it to, there we go, show up. Send to breakout rooms, open all rooms. So go ahead and chat through that. And Alexandria, looks like you're kind of getting bumped. A couple times, I'll send you in another room. See if it works.
Could you update the iClicker so it's on our phones or wherever we're looking at them?
That work?
Yeah, thank you.
Okay. And now can you jump out of that room, back into the room? Or Kat, did it send? Josh, what are you doing? Josh, why are you here? Taylor, you causing trouble?
What? How am I causing trouble?
Did you work in your group and then you bounce back here?
But yeah, I worked in a group.
Do I believe you? Sometimes I do.
I think I worked quite well.
I give myself a big pat on the back.
I deserve a cookie now.
Me too. I think after this is done, we should both have some cookies.
Oh yeah, for sure.
Oh, we have lab.
What?
We have lab after class.
Some of us have lab.
I mean, you can have a cookie between now and lab. Okay.
Yeah, it's not a stiff
I
drink.
allow
It's
it.
okay.
I didn't say that, but maybe that's my cookie.
I'm glad I don't have lab.
Okay, everybody's back. So this one was a little bit more difficult for a few reasons. One, I put Milla in there. Milla scares people, right? What does Milla mean? Problem is when you have too many people, it's hard to pick on someone. Verda, go ahead.
1,000?
I said it's 10 to the -3.
Yeah, great. So Verda and Tracy said 10 to the -3. So 1,000th or 10 to the -3. But the thing is, if we're using our Henderson-Hasselbalch equation, pH equals pKa plus log of concentration of base over concentration of acid. If both of these, top and bottom, are the same units, millimolar, then it cancels each other out. So the only thing that matters, and this is kind of the take-home message of today, the Henderson-Hasselbalch equation only cares about the relative concentration of the conjugate acid and base. It's not saying what is the overall molarity. Granted, once you get really, really, really small in your concentrations, then you start to be concerned. If you saw micromolar, Henderson-Hasselbalch equation might not work so well because then it's so dilute that you might not succeed in that 5% rule. So can I have someone, let's see, who can share? Kat, can you discuss how your group approached this particular problem and why it was challenging maybe?
I'm gonna be honest, I tried it myself just to see if I could because I left at some point while you were explaining it to go to the bathroom, so I missed a good portion of it. But the way I did it, I'm sure I didn't do too well, but I did 14 minus the pKa, then added the log of 0.25 divided by 0.50.
So here's, hold on a second, slow down, sorry, I'm trying to keep up with you. 14 minus the pKb.
Yeah, pKa.
And what does that give you?
That gives us,
That's
I got
10
10.81.
And then what is that number?
That number is the pH. Not
Is that
pH.
the,
Is it? I'm sorry, I don't know.
The pKa?
Yeah, the pKa.
pKa
Yeah, pKa. There we go. Sorry about
for
that.
ethyl ammonium. Fantastic. And then what did you do with that?
I just added it to the log of 0.25 divided by 0.30. Or, sorry,
Which one goes on top? Sorry, I wasn't.
36.0 divided by 12.0. I was looking at the number on my paper, was the wrong number.
Okay. So I love what you did. Your approach was, well, Henderson-Hasselbalch equation only uses the pKa, and with that one, it's a concentration of base over the acid. So you said, well, if I can find the pKa, then I should be able to find how the base over the acid influences the pH. And so if you go about this approach, you end up finding that if you have an equal mixture of the conjugate acid base pair, we would have a pH of 10.81. Are we going to be higher pH or a lower pH than that? Well, you're anticipating higher or lower pH than 10.81. I see higher, higher. Yep. So we have more of the base than we have. And remember, ammonium is a positively charged nitrogen with a proton to give up. So anytime you see ammonium in the name, it is always going to be the acid. So an amine is always going to be a base. An amine means a nitrogen with a lone pair of electrons that can act as a base. So in this case, I actually didn't do these numbers. I punched it in, 10.81 plus log of parentheses, 36.0 divided by 12.0 equals, so I found a pH of 11.2. How many sig figs do we have here? 3 sig figs, so 287. If we accidentally flipped things over, did something different, we're gonna end up finding a pH that would in fact have been lower than 10.81, which will tell us that we did something wrong. So what do we find in our numbers? Go ahead and stop this. Okay, we had some 11s, and then we had some 9s. So takeaway message, Henderson-Hasselbalch equation always stays the same. If you have the Ka, you can find the Kb. If you have the pKb, you can find the pKa. So you can convert back and forth between these. I think I do have 2 more listed here. So I'll send a screenshot. This is not a clicker question. I just sent it to you as a clicker question. So you have the screenshot. You can try doing both of these as practice for yourself. And the big takeaway is I want to make sure that you're able to predict the pH of a solution, talking about a conjugate acid base pair, and then to be able to figure out how to solve for the pH of a buffer using the Henderson-Hasselbalch equation and knowing kind of how it works. One logistics thing is, I think I mentioned in the beginning of class, going forward, I will have a waiting room set up for class. So as you come in, I'll have to let each person in. And that's just because some of my colleagues have been having issues with Zoom bombing, which never thought would be an issue. So keep that in mind. Also, if you're uncomfortable with any of this or the calculations or how this relates to lab, we're going to talk a bit more about that next week. But you can also just send me an email. We can set up a time to meet. I have a very flexible schedule. So tomorrow or Friday or possibly even this weekend sometime, I'm happy to meet with you to do a small office hours type thing. So please make sure you use that as an opportunity. If you have any questions, feel free to stay after class, and I'll talk to you guys soon.